Now, there's one thing that we should probably remember from our earlier days in physics. It's Ohm's law. And Ohm's law is that relationship between voltage, current, and resistance. But before we really get into it, I want to talk about what happens with resistance. When you increase resistance, talking about resistance increasing, so I'll sort of like draw that as an R with, I don't know, how can we show that a resistance is going up? Why don't we just draw it as an R with an up arrow? So as resistance goes up, we can say, well, what happens to the voltage? Remember, voltage is how much energy gets either produced or dissipated per amount of charge. So if you increase the resistance, well, you suppose that the amount of energy that gets used per amount of charge is going to also increase. It seems to me that the voltage across a big resistor is going to also increase. Resist that current more, use up more energy? Sure. But when the resistance of a circuit increases, let's just say it again, another variable that could be affected is the amount of current that flows. Now, think about this. If I have a pipe, here's a pipe, there's current flowing into it. Actually, maybe you can picture even a garden hose. Can you imagine if you take a garden hose and you pinch it off? So you constrict how much water can get through. You're pinching it off. Water can try to approach that constriction, that kink in the garden hose, but by kinking that garden hose, we've effectively increased the resistance of the garden hose to allowing water flow through. That means that only a trickle of water comes out the other side. So we can have a lot of pressure, but more resistance means less flow. And so that's what happens with electrical current too. If I increase the resistance in an electrical circuit, it actually takes down the current flow rate. The I decreases. So those are two ideas that come up when we talk about voltage, current, and resistance. So the way that people talk about it in terms of a proportionality is that resistance is directly proportional to voltage. And when I write this R alpha V, we're saying that resistance is directly proportional to electric potential difference or voltage. So increasing the resistance increases the voltage. And it's a linear relationship. What we're saying here is that if I increase the resistance, I will decrease the current. And so the way that we write that is that it's not proportional to the current. What we say is that it's inversely proportional to the current. Now, sometimes people will say resistance is proportional to 1 over I. You could also say current is proportional to 1 over R. But look at this. If that R in the denominator gets big, that means the current is going to get small. Resistance increases, current decreases. That's what this proportionality statement is saying. And we read this as resistance is inversely proportional to current. Resistance is inversely proportional to current. Now, if I take those two ideas and I bring them together, then I can relate resistance to current and voltage. And just proportionally, I could make the argument that resistance is going to be proportional to V divided by I. Now, I want to take it one step further, and in a minute, we're going to use graphing methods and actual data to show that these guys are not just proportional to each other, but in fact, resistance is equal to voltage divided by current. And we'll get at it using a graph and using slope, but that'll come in just a minute. But if I rearrange this equation, which hopefully y'all saw in an earlier grade, then I could write it as V is equal to IR. Voltage is equal to current times resistance, which I would be willing to bet, even though we kind of got at it using the idea of proportionalities this time, I'd be willing to bet that in a younger grade, this equation was just handed to you kind of mathematically as V is equal to IR. And they might have even slapped this label on it and called it Ohm's law. Now remember, R is resistance. Oops, let's make sure we're labeling the right variable. Resistance. And I bet you in that earlier grade, they said that the unit for resistance is ohms, and they used that Greek letter omega as the unit for ohms. I want to make sure that we're always looking at what's underneath the hood of these units. So ohms, if I look at this expression here, must have units buried inside of it of volts per amp. See how it's volts divided by amps? Of course, that could be written as volts is joules per coulomb, and amps is coulombs per second. And people say, well, does that simplify out to anything? Unfortunately, it really does not. A lot of the times, we like to make things kind of cancel out and look more beautiful for us. Let me just see where this goes, just to make sure that we're clear about this. Joules divided by coulombs, I'm going to do it in a different color, is in the numerator of that last line there. Coulombs over seconds would invert and become seconds over coulombs. You notice that the coulombs do not cancel out. And so we end up getting these terrible units of joule seconds per coulomb squared. And so this is one of those situations where unit analysis is great and everything, but I don't think that I really like expanding out ohms. And so basically very few people would even bother to do this. Possibly you could find a use for expanding out the ohms. We could look inside of joules and find that there's a kilogram meter squared per second squared buried in there, but I don't think I want to go any further with this one. This kind of just seems like an ugly exercise. So I think this is all true, but I think I'm just going to call it ohms from now on. Thank you very much. Anyway, let's take a look at the next bit, which is to set up this idea of an experiment involving a simple circuit. And we'll see this next bit as it comes.